This is part 2 of lecture 6 on wideband channel modeling. In part 1 of this lecture, I gave you an introduction to channel modeling. Statistical channel modeling was the most emphasis of that lecture, and in this second part I'm going to give you some specific examples. I will start with GSM model, and then I go to the JTC model, and we continue. These two models, I call it wideband models for wide area networks. GSM is for cellular system, JTC is for PCS networks, and both of them are I consider them like wide area network, though PCS systems are local in general. Some people call them local, but in my vocabulary, local is wireless LAN and WPAN, which comes as the next section. So for the first section, my example is model for GSM and model for the JTC, wideband models. Starting with GSM model, as I told you in the lecture 1, in this type of modeling, which is modeling for communication application, people define the standard with a scattering function, which is something like S of tau and lambda, and this is two function, Qs of tau and D of lambda. This is the Doppler spectrum, and then this is Qs of tau. The Doppler spectrum, they give it something like this. For example, in the GSM model, they have two of them. One is classical and one is Ricean. This classical one is nothing but like double ear thing that we have seen before. FM is the maximum frequency. And the second one, the Ricean, is the double ear plus an impulse at location 0.7 of FM, which is somewhere in here. This one, if you remember, classical is equivalent to Rayleigh fading. So this is Rayleigh. And difference between Rayleigh and Ricean was a DC component. Ricean is a Rayleigh with DC component. This is that DC component. So if you simulate your channel, actually, if it is Ricean, you have a DC component plus Rayleigh variations. And this is the DC, and this is the Rayleigh variations, which is similar to the other one. Okay? And you calculate FM by velocity divided by lambda, which is Vm over C times Fc, that we have seen many, many times. Now, so this is one part of the definition. I have to define two functions. My Doppler spectrum is defined in here. How about Qs of tau, which was delay power spectrum? I told you in part A that in traditional standardization activities, Qs of tau is defined by something like this, by a bunch of impulses with location, tau I, and magnitude square, if you want to call it, of that particular pulse. Often they give you tables for that because they know that the shape is like this. Now, this is a typical, in fact, example which is used by GSM, old GSM models. They give you two possible choices. One is implemented with 6 taps. The other one is implemented with 4 taps. Now, these are the time of arrival of the taps for the model 2, time of arrival for model 1. Okay? And these are the power associated to each of them. So the first path is 0 dBm. Usually they normalize it to 0. The next one is like 4 dB below. The next one is 8 dB below, 12 dB below, 16 dB, 15, 20 dB below. And then for the second model, so that was model 1. This is model 2, is 0 dB, 2 dB below, 10 dB below, and 20 dB below. And always the first path is assumed to be Ricean, because they assume that there is some line of sight associated to that. And other paths are obstructed line of sight, so they are classic or Rayleigh. I mean, in terms of implementation, means that if you want to simulate these classical ones, you simulate them the same way that you simulated in project number 1. And if you are simulating the first one, you do the project number 1 plus a DC component. How much is that DC component? Is this guy. That's it. So you can simulate a bunch of taps separately. And then you can put some delay for them and add them up. Okay? So basically the same Jake model that we had for simulation, or like we had like filtered Gaussian noise, I will do several of them, either 4 of them or I do 6 of them. And I add them at different delays. How do I create the delay in the MATLAB? That's very easy. That's mathematical. I put the delay. How do I create the delay with hardware? I put a D flip-flop or a delay line between different paths. So how many delay lines I need? I need one at this, point 1, the second one, point 2, point 3, point 4, point 5. So I have like a tap delay line with 5 taps. Okay, so I will have something like signal comes in and goes in a delay which is equivalent to 0.1 microsecond, and then I have my first tap, okay, and then I have another delay of the same amount. So in here is my second tap, another delay of this similar thing, and I have the third tap, and so it's my first tap, second tap, third tap, and then I have fourth and fifth tap. Each of these taps are how much? Are 0.1 microsecond. And then the first one is multiplied with equivalent to 0 dBm, which is 1. Okay? 1, which is 0 dB or dBm, whatever. The second one is second one is 4 dB below that. 4 dB below that is like 1/4. 4 dB is not 1/4. No, I will calculate it. I have to calculate it. 4 dB, because 3 dB is 2 times. 4 is like something like, I believe, 3 times, something like that. I don't know. You have to just calculate it. But I find that. So this one, this tap comes like 4 dB below, -4. The next one is like whatever it was, like another 4 dB under that. So I multiplied with that value. This is -8 dB, -4 dB, and then etc. The next one is -12 dB. The next one is -16 dB. And the last one is -20 dB. I mean equivalent to -20 dB. And I take all of these things, I add them up, and this is my output. So input comes in here, x of t, and this is my y of t, which is the output. And this is the hardware implementation of JTC model with 6 taps. Now you can see why people give you 2 options. You have 6 tap option, 4 tap option. Simpler to implement. But you try to keep the RMS delay spread the same. Okay? So you have like 2 options to implement it. Okay? So basically, if I want to look at the impulse response of this, so there are different ways to look at that. Impulse response is something like this. This is 0. Then at 0.1, I have like -4. These are in dB. At point 2, I have minus 8. Then I have minus 12. At point 3, minus 16 and minus 20. That's whatever. So at 0, 1, 2, 3, 4, and 5. Huh? This is what? This is my Q sub tau. A sketch of my Q sub tau, which is equivalent to that table that I have, introduced by the. So basically, if you want, I have like for the first tap in here with 0 dBm that I had, this is Ricean. Means that when I want to simulate the variation, this is my like variance. Variance is like 1. And then I have some DC component on top. So I do the same simulation that I did in the first, like Jake model or the Gaussian model that I did in my project number 4. And I put the variance like that. And then for the second one, I put 4 dB less variance. But I don't have the DC component anymore. I'm exactly what I had before. And then for this one, minus 8, minus da, 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 da. So I call the same subroutine like 5 times, and then I change the variances. Only for the first one, in addition to variance, I'm adding what? A DC component to make it Ricean. And then output in here is a channel impulse response. How does this channel impulse response looks like? If you sketch it, it's not like this thing. This is the average of this thing. You sketch it, there are a bunch of these guys which are going up and down. If you look into the videos that I have, they show you, I think, some of these variations of the channel. Some simulations are in some of my labs. If you go to the website, I have the laboratory on real-time channel simulation. One of those laboratories shows you the variation, simulation after variation. So all these tabs are going up and down all the time. How do they go up and down? According to the Rice or Rayleigh, which we call it like classic. Okay, so this is how I'm simulating the channel impulse response. They are just changing in time all the time according to the Jake or Jake plus DC, which is the Ricean. And that's it. That's how I simulate the JTC model then. Who wants to simulate this? The guy who designs the modem. He wants to see that what is the effect of multipath on their modem. Now, if they have designed it on the piece of hardware, they implement this model in what? In a piece of channel simulator, like PropSim, for example, that we saw in previous, previous lectures. Or they do like simulation on the MATLAB or whatever to just calculate it. Or simulate it. So either for simulation in the hardware or in the software, I can implement the channel. And why do I want to do this? Because different companies are coming with different proposals, and I want to just do a comparative performance evaluation. Also, I want to give a guideline to manufacturers to have certain reference point for their design, to tweak their design, to make sure that everything is operating properly. If I have a model like that, then I can give you some expected performance evaluations, and you can run against that expected performance evaluation. Now, so this was my first model and the most detailed model. If you come in this model, what I did, I modeled D lambda. Oops, I shouldn't do that with this. But we have to clean it later on. Now I will model D lambda by these functions in here, and Q sub tau I defined it with this table. The Q sub taus that I have, if you sketch them, I have two Q sub tau. One is this, and one is this one. This is 4-tap model. This is 6-tap model. Okay, and with that I have like the model. And when I implement them, each of these taps are like moving up and down all the time they are moving up and down. That's the first model. Okay. Now, what they do in the standardization activities, how do they come up with this type of thing? They go outside, they do wideband channel models, channel measurements, and they measure the tau RMSs. So the tau RMS that they get, they try to fit these like channel profiles so that tau RMS of the channel profile fits the tau RMS of the measured environment. Okay. So, but for GSM, I take a car, I walk around, I measure the channel impulse responses, and for them, I will calculate associated tau RMSs. And then I come in there and I say, okay, I have like one tough model, for example, which are in like downtown areas, and then I have another soft model, which is for open areas. For open areas, I have one profile. For tough areas, I have another profile. For a small city, I have one. For large city, I have another one. So a lot of measurement is going to be translated to one channel profile, which represents a class of buildings or a class of like areas, if you want to call. Let's go to another model. The other model is JTC model, which I like. JTC model, I have like perhaps some bias on that. But in JTC model, they come and, I mean, I saw the principle in the GSM example. That principle is that I'm defining a Q sub tau, I'm defining a D sub lambda, and that's it. And then people can go and simulate. Okay. Now, this Q sub tau, which is the important one that I have in there, is related to really tau RMS. I mean, if I change the tau RMS, I change the Q sub tau, really, in a sense. For any Q sub tau, for any tau RMS, I end up with a different channel profile, I call it. Now, and on the other hand, if I have an application, for example, for that particular application, I have different scenarios, different areas. Associated to these areas, I will define different tau RMSs. This is a complete good example that is done by JTC. What is in here is they have divided, as we have seen before in JTC, they divided the buildings into residential, office, and commercial. You remember that. They did that for the path loss model. Then for the outdoor, they divided with outdoor urban high-rise and urban low-rise. And then they had outdoor residential, outdoor urban high-rise, and outdoor urban low-rise with high antennas. Okay, so I have 3 high antennas, 3 low antennas, and then outdoor I have 3 areas: high-rise, low-rise, and residential areas. High-rise is downtown areas, low-rise small cities, residential is like residential areas, like suburban areas. Okay. Low antenna. Do you remember what was the meaning of low antenna in JTC? Do you remember that? Antennas were not on the roof. They were under the roof, on the walls. Okay. High antennas are above the roofs. Okay. So they had different like models for that. And they are only holding for outdoor areas, because in indoor areas always antennas are installed what? Inside. Okay, maybe on the ceiling or the wall doesn't make much of a difference really. But when you go on top of the buildings, it makes a lot of difference. Or it's on the side of the buildings, because the signal doesn't go through the building. So based on this classification that they have done, they are coming to another class of classification. They say if you have residential houses, now I pick up like 100 residential houses and I go and I do measurements in them. Are you expecting to have the same RMS in all of them? In all the areas? No. You will have like different, like houses. If you are in the smaller areas, local areas, you may have a smaller. And then you may have bad buildings in which you have much higher values. So they specify three things. Channel A, B, C. In the A, RMS delay spread is 20. It's like line of sight really. B is like 70, which is like a regular residential. 150 is like a very tough house, a lot of metallic objects in there. Then they do the same thing for offices. So they give you three things. So you have good, medium, and bad. Okay? And then they continue that for low rise, high rise, and for all of them they define this table. Now, for each individual entry in here, you need now a table similar to this table that I had, like these profiles or like this table. You need something like that. Okay? They define those. If you go inside the book, these are the things. Table 6.4 gives for these three different residential houses. Gives you the what? Gives you Q sub tau, which is a figure like this, equivalent to a figure like that. Okay? And then if you come for like office, it's this table, etc., etc., etc. So each entry in here is an impulse response, okay, which has this tau RMS for that. Now you get one example, for example, this one, which is the one that was my example in the book. You have three impulse responses, or three, not impulse responses, delayed three Q sub taus, which is impulse response square, delay power spectrums. And these three, one of them has RMS value of 150, the other one 70, the other one 20. And if you look at those and sketch them, for example, out of the table 6.4, you get something like this. These are the sketches. Okay? This is the good one with tau RMS of 20. This is the medium one with the tau RMS of 70. And this is the bad guy with tau RMS of 150.
How do you calculate the tau RMS from the
tau RMS,
picture?
if you get Q sub tau, we have equations for that. And you did it actually already.
Okay.
You did it in one of your exercises. In homework, I don't know, homework 2 or 3, you did it. So there is Q sub tau equals to a square root of like tau minus tau i's. You use that equation and you find tau RMS. Now, this is the table, which is the same as that other guy. But this table now, rather than giving two paths, it gives you two locations and two magnitudes. That's exactly equivalent to what I have in here. First one 0, the other one minus 13 under that. Okay? So each entry that I have in here in the table, each of these is one impulse response. This is this one, and then this is the one with the 4, and this is the one with the 6. Now, so, and if you take these guys and put it in the equations, and you calculate tau RMSs, you end up with this one, which is what? Which was like 150 nanosecond. This one was 70. This one was 20. Now, the only thing is that, okay, now I know everything, and I can go and design that tap delay line. If I want to go for this one, I need only one delay. How much is that delay? Delay is like 100 nanosecond, okay? And then the first one is multiplied with 0 dB, and the next one is multiplied with what? 13 minus 13.8 dB. And then you add them up together, and this is your output. This is your input, this is your output. Y and X. Here I am. So this is chance. But the only thing that now you want to know is that what is the delay power spectrum? Why do you need the delay power spectrum or Doppler spectrum? Sorry, what is the Doppler spectrum of this? Why do you need that? What was Doppler spectrum? In order to simulate now this thing, this coefficient, which is multiplied with that, I have a filter and I run the filter with what? With Gaussian noise. And the output of that thing is this number that I multiply in here. Is that right? What is the specification of this filter? It's flat. In the indoor areas, according to who? According to JTC model. But for the GSM model, it was not flat. It was Ricean, which was this, or Rayleigh, which was like this. So these are a specification of simulation for each tap. Okay? That's the type of filter that you use for the simulation. So with the knowledge that we have so far, we can simulate all of these channel models, whichever that we want, for whichever application that we have. We will have like a project on that, project 3, which I assign it later on. So what is the Doppler spectrum? Flat Doppler spectrum is this thing, which basically is like flat between FM and minus FM. What is the FM? We have seen it many times. This is the FM. This is the FM. Depends on my velocity. When I'm in indoor areas, do you remember what was the FM? In indoor areas, typical FM was how much? Around 5 to 10 hertz, because you cannot move faster than that. When you go outdoor, however, and you have car, it may go up to 100 or maybe even more than that. But you can calculate it very simply. But remember that if I'm in the indoor, I cannot drive a car indoor. That's the purpose. So always I'm small. Okay? So this is now a more elaborate model that I like. Okay? Because what? It's comprehensive. It is covering a spectrum of buildings. And I mean, indoor and outdoor actually, not only building. It covers a spectrum of areas, indoor and outdoor, and different antenna configurations. So this is a very comprehensive one. And also for each of these entities that they identify, they don't stay with one model. They stay with 3. Good, medium, and bad. So that's why I like this model. Okay. That's about like models that I talked about for wideband areas. Okay. So basically, up to here, I gave you 2 examples, which were 2 models. One was GSM model, and the other one was JTC model. Now, I would like to close this video, and then I start to talk about 2 more models, 2 or 3 more models, which are used for local area networks.